let's wait 1 or 2 minutes, few minutes before we start. But in the meantime, if you have any question, feel free to ask at the moment. Okay, I guess we're all here, so at least most of you are here. So I think we should get started. Okay, let's review a little bit. Last class, what we have covered. So the starting of the last class is the beginning of what we call the statistical inference. You can make a decision, okay? And decisions start from learning how to do sampling, okay? Or what sampling from the population, what we get from there, okay? And we first start from simple random sample, which essentially said if you trying to make sure that equal probability being selected and each select independently, okay? So what it means is every observation of same mean and same variance and covariance are 0. Okay, and do note that this actually have implication saying the expected xi times xj, sorry, will have implication say xi times xj will be equal to expectation of sum is expectation product will be product of the expectation. You can separate them. The reason why this is true is because covariance x and y can be written as expected x and y minus expected x times expected y, and this is 0. They're the same. Okay, so that is something we will be using later in this class, so don't worry about you don't get it. It will be used again. So the sample mean is the mean of sample, or expectation is a arithmetic average, right? It's average or mean of the average. Okay, and turn out to be the mean of the sample mean is the population mean, right? And this unbiasedness, we will talk about it very soon. Okay, and what we have shown is the mean of the sample mean is the population mean, and the variance of the sample mean is same as the population variance over n. So that's a little bit tricky part here, depend on sample size, right? Because when n get larger and larger, you should get more accurate estimate, right? And that should be the same. Okay, so that is the one idea behind. Okay. And the central limit theorem essentially said when you have n gets larger, the sample mean, okay, we know this too already. Okay, the additional fact is normal distribution, and the interesting point is here is this, the underlying distribution can be anything, okay, can be any weird shape, but at the end this x bar with a bell shape. Okay, no matter what x is, okay, no matter what you're drawing from, turn out this is the same thing. Okay, I hope that's clear. And the other thing that goes on is the case of proportion, where you have certain one, and in that case the variance is much easier because by the virtue of binomial, this the mean and the variance are related. I think we should add to make it more clear. By definition, this is pi. Okay. Because this follows from the expected value equal to the mean. Okay. Same as the variance and standard error. Okay. And central limit theorem applies very well when n pi and n times 1 minus pi are 5, at least 5. Okay. And lastly, we talk about this result, which said this is very useful central limit theorem, right? But this guy is not known. Okay. Then what can we do about that? If we replace by s, right? And this turned out to be, right, T distribution with n minus 1 degree of freedom, right? So that is first reason why S is n minus 1. Okay. you need to use n minus 1 to achieve this result. Okay. So this is the first justification. We will give another justification very soon, but this is the first result we have. Okay. So we'll use this again at the end of our class today. Okay. So don't worry about that. This one we'll be using again. So this is what I have just said. So what I want to say is to prove this result, why this is true. Okay. But the proof will rely on two results that we never prove are in our class. Okay. So we'll use two fact property or two fact. We stay with the proof. Actually, it should be proof. Okay. So what's the two fact? Fact number 1 and fact number 2. Okay. So first is they are random variable from normal mu sigma square, and this is the sample mean. This is the sample variance. Okay. The first result we said is sum of xi over sigma. Okay, is chi-square d group n minus 1. Okay, and we don't explain why this is true, but that is it. Okay. Okay, and turn out S and X are independent. Okay, that is pretty amazing though, because X are sum of the X, and this is the also X, right? And turn out these are independent. Okay, it's pretty surprising. Okay, why? Okay, it's not easy to explain why, but turn out they are independent. Okay, so it's something interesting, saying that give me the X bar. Okay, I do not have no X bar actually don't help us to know any variance. Actually, it's not that much surprising in some sense. It's like you tell me the mean. Okay, can I have more guess on the sample variance? No, right? You give me sample variance, can I guess the mean? No, not really, right? So it's some kind of like, because of the normal, right? In the normal, the mean and the variance are unrelated, right? It's not true, say, for Poisson, right? I know my mean and I know my variance, right? Because I know the mean equal to variance, right? If it's binomial, I know my mean, then I know my variance again, right? Because that is related in that sense, right? Because one is NP, one is NP times 1 minus P. So I know, if I know my mean, then I probably know my variance, somewhat know my variance. But for normal, knowing my mean, yeah, not really helping the variance. Okay, you can understand in that way. But anyway, let's go ahead. We're going to prove that's the case. Okay, so first, let's see what is this guy. Okay, this guy. Okay, in particular the S, right, is this guy, right, the sample variance. Okay, and we have said this is first property is chi-square, is a chi-square d group of n minus 1. Okay, so that is the case. Okay, this is something we want. S over n is chi-square n minus 1. And the second property is the independent. Okay, and we also know that this is standard normal. Okay, this is from the assumption we have, right? Now, why this is T? Okay, first you multiply and subtract, you divide denominator and numerator by sigma. Okay, okay, and the numerator here, I use other color for you to see more clearly. The numerator, okay, is from here, tells you this is Z, right? It's normal CO1. Okay, and the denominator here, which we are proving, Actually, it's chi-square n minus 1 over n minus 1, okay? So this is exactly what we mean by t distribution, right? It's normal over square root of chi-square over its degree of freedom, right? This is what actually it means, right? Because t of m is z over chi-square m over m, okay? So that is exactly why this is t. Is that okay? So there's nothing proved, but just trying to show you this fit the definition. Of course, these two property, we didn't show it, right? We just say this is right, but if you go further, if you want to know why this is true, you need to go further. But for the moment, we just, this is what we have. Any question? First question is, what is different between mu and x bar? No, mu is a population here. Okay. Oh, sorry. Population here. You have many data. Okay. All the data, you sum all the data divided by n is mu. Okay. It's population average. Okay. Now consider a sample. You draw a sample out of it. Okay. You draw a sample of it. Sample. The sampling. Okay. And the sample will have some observation here again, right? We have to draw some sample, and the average of this sample is x bar, okay? And the mu is, the population is unchanged, right? The population is there, the value is there, there's no probability there, okay? And but sample, depend on what you draw, this value, what the value you draw, this x bar will be a random variable, okay? And this is the mean of the sample, is a random variable, okay? And the mu is something, say, income of the population, okay? It's something that there's a value there, does not change, okay? Depend on what you drawn from the population, it changes accordingly. So that is a random variable. And how to compute t? Yes, that will be, I think we covered this, is how to compute t is from the Excel, right? The norm as inward, right? We have t inward, same as a norm as this. We also have t as this, same thing. That's not computational. It's Excel will give you the answer. And for those who, is it okay, Peter? So it's also a bell shape, but it's more, the tail is heavier, and t is with n, and if you can show if n go to infinity, t will converge to normal 0, 1. Okay, it's a bell shape, but a little bit more flatter, something like that. If you forget, you can go back to the slide when we talk about the continuous distribution, where we talk about the t. Is there any further question I can help? Any? If no, then we will start our next set of slides. Is there any question? No? Okay. Then let's start with the estimation. Can you see my slide estimation? So let's get started. So so estimation, okay, we just, I think it's very useful to have this graph, right? The population, okay, and there are some observation here, okay? And then what we want is, we want to study some property of this, okay? We maybe want to know the mean of the population, right? We want to know mean, okay? We denote as mu, right? Or sometimes we want to know variance, okay? Why you care about this, right? For those who do finance, right? You want to care about what is the mean return, right? Or the variance, right? Of the return of the stock, right? So that's something you care, right? You want to guess these two especially, right? And something we want to do, sometimes we, in the notation of estimation, we will call theta as what we call the variable interest, or the variable that is interesting to us, okay? And but what we actually do is we have to have some way to guess it, right? So what I do is you pick up some sample here, right? You are sampling, right? The sample, okay? Sample will be just some observation, okay? And how to guess these two, right? And we know our natural guess for mu and variance. So far, you learned so many, right? Is the mean, sample mean mu, okay? X bar, and X bar coming from here is the average of the sample, okay? We want to usually use this to guess this, right? This is something, what we do is do this to guess this guy, to guess, okay? And this guess, we will call this guess because this guess would depends on what you draw, right? Because each time the sampling is different, okay? So how, this is the way that I try to guess this. We will call this estimator. Why is it estimator? Because this is a, we can imagine it's a rule that try to guess it, right? It's a way to guess it. It's estimator, right? And this is estimator. It's a random variable. The reason why random variable because it depends on the sample you draw. Okay, different sample will result in different sample mean, and that means the different guesses we have. And usually this depends on the sample size. So that's why we denote the sample is usually called het. It's a theta het. And of n, because usually depend on n. It's function of n, you can say. And an estimate is a realized value, okay? Maybe 3 or 4 or 5. Once you draw the sample, you calculate the value, it becomes estimate, which is no longer a random variable, okay? Estimate is a random variable, estimate is not. Is it okay? Up to this now. Okay, have to distinguish what's estimator or estimate. So this is the way you can imagine, this is the way to estimate. This is exactly the value. This is same as this is a function, right? This is the functional value. If you want to have a parallel idea, okay? Now, what we want to distinguish the two is the point estimator and interval estimator. So there will be the two key parts of this chapter. The first part we focus on is the point estimator. The second part will be the interval estimator. We'll cover both this class. Okay. The difference is the first one is give us a number. The second one, it means it give an interval. Okay. So what do we mean by these two? A number like sample mean is actually give us a number directly, right? That's what's the guess? Say what's the guess of today's Hang Seng Index? Maybe number X. Okay, this is a point estimate. Okay, usually when you look at the security report, right, and they say, oh, the target price is $35. Okay, say, okay, and that would be point estimate. But if the target price is between 34 to 36, okay, it's not a number, it's between 34 to 36, right? Instead of 35, okay? So this is called the interval estimate, okay? This is the point estimate, right? This is the point estimate. Okay, then this is the interval estimate, right? Okay, so that is the difference between the two. Is that clear? So we focus on first was point estimate. The second one is the interval estimate. Is that clear? What we are doing today? By the way, although we finished the topic of sampling distribution, we don't have quiz next class because I think that chapter is too short to have a quiz. I think we will combine with the estimator to do together. Okay, because we're slightly behind the schedule, but after this class we will be making our schedule back. So it's not. So that's why we are saving half the class to combine the two quiz together. So we will have one less quiz, I guess. Okay. So any question? If no, then we go to the next slide. Point estimator. Okay, point estimator. So you notice that's slightly different from your slide because I think I changed the consistency. I move it to technical. There's only difference. So the consistency, I move it to the next slide. I move the next slide. Okay, I changed the technical slide because that would be actually we don't. I think we don't need it for the course, but it's good to know it. Okay, I just put it in the technical slide. I noticed that life will be easier. To cut it. Okay, so unbiasedness, which means that the expected value of the estimator is the parameter we want to guess. Okay, actually what it means is expected value is equal to itself. Okay, so what does that mean? It means that suppose this is we want to estimate. Okay, but what we get is something like here, right? Depends on what you draw, right? It can be here, can be here, can be here, can be here, can be a lot. Depends on what sample we draw, but average of those will be same as what we want to guess. Okay, it's not saying we hit the target. Okay, but it's saying that if you repeat this many times, we don't do it. We just do one. But suppose we do it many times. We do many sample, and we repeat this estimate. Okay, average of the estimate. Okay, will be the parameter with the estimate. Okay, what it means is suppose we have we want to guess sample. We want to guess the mean of the population, and we can do a lot of sample, and each sample will give us a 1 sample mean, 2 sample mean, 3 sample mean, and many sample mean, and average of this sample mean is the population mean. Okay, add them all up, and divide by n is exactly what we want. Okay, it means on average we target, but doesn't mean anything about we do target. Okay, so this is somewhat very minimal requirement, right? Is on average hit it. Okay, so we want it at least to be true, but the second one is about efficiency. Okay, based on unbiasedness. Okay, if they're unbiased, okay, we are saying they're more efficient. A is more efficient than B if A has less variance than B. Okay, what does that mean? It means the following. So we want to guess this. Okay, and blue is more efficient, right? If blue is here, okay, maybe here, okay, it's A, okay, and the green is B, okay, B maybe here, okay, sample here, okay. B is on average also hit the target, okay, but it's more further away from the target. Okay, it's how accurate it is. The more accurate, it's more efficient. Okay, so these two criteria we'll use to justify the following. First, as you show in the next slide, we will show X bar is an unbiased estimator of mu. Actually, we have shown it, okay? And we'll also show this, the variance of X bar is less than the variance of X bar of weighted average, okay? This is a simple mean, simple average, mean, arithmetic mean. If you look at other weighted mean, okay, it is other weighted mean has higher variance, okay? So that's why we just add them up divided by n, okay? So that explains why we want to use X bar. The second thing we want to show today will be, you want to show this sample variance, okay? The sample variance is n-1, okay? This guy, okay? This guy is unbiased, okay? This is the two fact we're going to show, okay? The reason I will give you the explanation why we need n over n-1, right? Instead of over n, okay? If you use this guy, that means if you use this guy, okay, it will be not equal to what we want to estimate. Okay, is that clear? What we're going to do? There's no further question. Let's go. So as I said, I've moved this to the technical part. Is what we call consistency. Consistency means the limit of the estimator is the problem itself, which means that if you get higher and higher n, then actually we will get into our goal, okay? So what it means is, suppose this is the theta, okay? And what it means is, when n is small, it might be here, here, okay? And when n get bigger, then it will be closer. And at the end of the day, when you get even smaller, it will become closer and closer. And at the end, you have very high n, everything will be here, okay? There's no variation. When you get n is bigger and bigger, you exactly hit our target. Okay, is that clear? But I think this is more technical with a limit, so that's why I move it to the technical, because I think that I just taught the other section and then they have difficulty understanding the limit, so that's why I just move it here to avoid you feel technical. Any question? So the sample mean and sample variance, okay? And as we said, they're natural estimator. When we have just have defined it. So let's prove the thing we're going to prove right now, okay? First, I think we have shown in the last class, okay, why this is true. Okay, maybe I just prove again, the whiteboard again, okay? Why this is true. So this is equal to summation of xi over n, right? So that means expected x bar will be expected summation xi, sorry, xi I smaller over n, okay? And 1 over n can be taken out, so 1 over n expected summation xi, okay? And expectation you can put inside expectation, so 1 over n summation expected xi, okay? And because simple random sample, these are all mu, okay? So summation of mu, and the n of them, so n mu, so that is mu. Okay, so that is the proof of why expected x bar is mu. Okay, I think we proved in the last class. So what we actually want to show you now is actually this more general, not even this. We can show this weighted average, any weighted mean is also unbiased. Okay, so why is the case? So let's see why it's the case. Okay, is expected summation wi xi over summation wi. Okay, sum of all the weights is a constant, so can take out because it's not random variable, so it's a constant. Okay, and the next step will be expected value can put inside the summation. Summation expected mu I xi, okay, and expectation can be put further, one more step. Okay, and this is mu, okay, and all mu can be taken out and they cancel out, right? So that's, you can write this. Mu, so cancel out, just mu. Okay, so this, the weighted mean is also unbiased. Okay, so why we use this instead of this, right? Because they're equally good. Okay, so now we're going to give you the reason why this is true, and after this we'll break. Any question before I proceed? Is that okay? No question? Good. Let's go back to the slide. Now, we want to show at the end of the day, as you expect, the variance of this weighted mean is bigger than the variance of the simple average. Okay, that is what we want to do. Okay, to make our notation easier, we can make the weighting, normalize the weighting everything to 1, and you will be, this will be same as any weighting, right? Because you just redefine any weights to be weights over the summation of weights. Okay, this will give you the same result. If this weight is not equal to 1, you can redefine this way. Okay, this normalization. Okay, so now here we have the variance of this weighted sum, okay, weighted average. And the variance can go inside. Okay, why? Because any x are independent. Okay, so that's why variance of sum is sum of the variance if they're independent. Okay, and the second, here to here, how you jump from here, why you can take this out with square, because we have known this is the case, right? Variance a of x, right, is a square variance x. Okay, so that means this can be taken out. Okay, and this guy, right, variance of each observation, right, by simple random sample, this is sigma square. Okay, and that's why we have this sigma square. And this sigma square is for each one, so sigma square can be taken out. Okay, so we have this one. So what we want is to show this is bigger than this one. Okay, to show this one, we have to rely on something what we call, if you learn complicated, I mean not complicated math, but you learn the advanced math, right? What we know will be Cauchy-Schwarz inequality. Okay, we won't prove it, okay, but we will show you the following. Okay, Cauchy-Schwarz inequality is the following. Let me use the other bedboard to explain what it is. Maybe I can clean this up. Okay, Cauchy-Schwarz inequality is like this. Okay, suppose you have bunch of number u1, u2 up to un. Okay, another bunch of number v1, v2 up to vn. Okay, there are two set of equal numbers. So Cauchy-Schwarz inequality said the following. Okay, it says sum of the square of the first sequence, okay, which is u1 square plus u2 square plus un square. Okay, this multiplied by v1 square, v2 square, okay, sum of the square, okay, will be bigger or equal to, okay, each one you multiply them together, u1 v1, u2 v2 up to un vn square. Okay, to prove this, if you learn advanced math, that will you learn it for a class to prove why this is true. Okay, if you start from algebra, but if you start from vector, then it will be much easier. Okay, but we are not going to prove why this is true. This is a well-known result proven in mathematics. Okay, we're not going to prove this is why this is true. Okay, but we use it. Okay, now how we use it is we will say u are omega w1, w2 up to wn. Okay, and v are constant 1, 1, 1, 1, 1, 1, 1, because Cauchy-Schwarz inequality apply to any number, any real number, but of course it also apply to complex number if I remember correctly. But anyway, it applies to constant too. Okay. In this case, we have the left-hand side will be omega 1 square, omega 2 square, omega n square times 1 square, 1 square, 1 square. Okay, it's bigger than 1 times omega 1, omega 1, omega 2 up to omega n square. Okay, so this is sum of omega I squared, and this part is n, right? And this is 1 because sum of all the weight are 1, okay? So that's why sum of all the weighted square is bigger than 1 over n. Is that clear what the causes was in the quality bias? Okay, so that is what we want to prove. Go back to the slide. Okay, so this one you know so, and this is bigger than 1 over n, and this is the variance sample mean. This is the variance of the weighted average. Okay, so sample mean is good. That's what we want to say. Okay, with a break of 50 minutes, we'll come back on 11:36. Break now. So I see you. Feel free to ask me any question in the chat. Someone asked me why the right-hand side, the formula equal to n equal to n minus n over 1. Let me see. Let me show you the screen. Are you asking why this n over 1? Oh, that is what we have just shown. The sum of the Cauchy-Schwarz inequality is bigger than 1 over n. That is, I think, the whiteboard we've written here. Sum of this bigger than 1 over n. Someone asked me, can I upload the record thing? I think every record is there. No? I think it's already in the Blackboard. It's not there? I think it's there, right? Oh, I see. I didn't write that down. Okay, sorry. Input. I think upload it, but I forget to. Thanks for telling me. Let me upload it. I think upload it. I just put the link there. It's surprising. I didn't. Oh, sorry. For some reason, I mean, I don't know why, but yeah, it's already updated in the Blackboard. Tang Ning, is it okay? Peter, page 20 of the sampling. So someone asked me the let me see. Peter, are you asking this question? To Peter, please ask question. Yes. You may open your mic or you can type it there. Some difference for what? Yeah, okay, approximate, but there's some difference, yeah, but the difference is very minor, right? I think. Yeah, you can approximate. When n is about 100 or something, then the t and z will be not much different. So, I mean, I guess probably this is this. I mean, I can go back to the slide about the random variable. I think we have shown somewhere, I didn't show it, but you can see when t is 20 is already very close. Green ones, can you see the graph? When green is 20 is very close to the infinity. So that's why you try to check. Actually, you can check from Excel by yourself. You can check when t is about 100, I mean, actually about 60 or 70, then it's not too much different. So usually t would be interesting when sample size is small, and say when the sample size is more than 700, then in that particular case it's not much difference though. So t and z would be very similar. Okay. I think we can resume. So we just prove this part. So we want to show you why this very important idea, because I think many of you have to query why we use n-1 here. Okay. So this is what we're going to show. Okay. We will actually show this is true. Okay. So that's why we use sample variance all the time is n-1. This white Excel is n-1, not n. Okay. So that's the goal. Is that clear what we're doing? Okay. There will be some math, but I hope that should not be an issue. Okay. So let's get started. Okay. So remember, the goal is we want to show this guy. Okay. This is the goal. Okay. So how do we proceed? So we proceed by writing the definition, right? Expected s squared is expected 1 over n-1, right? Summation xi minus x bar square, okay? And this 1 over n can be taken out, right? So that's the first step. Now the second step, I use another color, is a minus b squared is a squared minus 2ab plus b squared. A squared 2ab b squared. Okay? Is that okay? Okay. The next step is summation of this, right? And there is not too much different each one, okay? There's no difference from each one, so you can just write n of those. will not be different. Okay, and I guess this should be, I should write in, maybe I should do it in the some technical thing. I think I should write down there. So let me write that down. That would be better. That would be more clear, I think. So it will be n minus 1 summation xi minus x bar square, and n minus 1 taken out is 1 over n minus 1 expected the summation xi minus x bar square. Okay, just take one out, and there's a square plus b square, as we just said, will be xi squared minus 2x bar xi plus x bar square. Okay, and what we're doing is, because summation, we can take the expectation in. Summation expectation of xi squared 2 minus x bar xi plus x bar square. Okay, and then you can put this one by one. Okay, and this it'll be xi square. Okay, and because they're the same for each one, so that's why I dropped the subscript I. Okay, and it will be expected 2 x bar xi. Okay, and this is expected x bar square. Okay, and this is a constant, can be taken out. Okay, so this should be 2 bar expected xi. This again is x bar. Okay, so that's why you have 2 x bar square plus x bar square plus this, and then your summation. Okay, and there are n of them, so there would plus x bar minus x bar would be minus x bar. Okay, so that's why from here you go back to the slide, right? Minus n plus n, so we n ex bar expected x. Okay, and what you can see here, n is here. Okay, take out the n. Okay, and what you have is this 2 number. Okay, so the next part is, first we want to check out what is this particular guy. Okay, what is expected value of the x bar square? Okay, expected value of the square of the mean, sample mean. Okay, so that's what we're going to do. Is that okay what we're doing? Is that okay? So how do you solve this? It's not terribly complicated, just some algebra here. So here, what do you mean by this? What is square, right? So we write this is the x bar, right? It's the x bar square. Okay, and you know that a b square is a square b square, right? So that means you have 1 over n square expected xi squared. Okay, and 1 over n squared you can take out, right? Become 1 over n. This is here. Okay, and how do you calculate this guy, right? What's this guy? Is x1 plus x2 plus xn squared. Okay, how to figure this out? Okay, we can use what we call the table method, right? Probably you learned this from your high school. So x1, x2, xn, right? And x1, x2 up to xn, right? Because you take x1, multiply that with everything there, right? x2 must, because this is what you do, right? x1, x2, xn times x1, x2 up to xn, right? That's called the distributive law, right? You just take the first thing, you multiply by this guy, multiply that guy, multiply by this up to the other one, right? And then you take this, multiply the first guy, multiply everything, right? Just like this, multiply everything up, multiply this everything up, right? So you do notice that there will be n square of number, right? And the notice that this diagonal are all square, x1 square, x2 square, are all xn square, okay? Diagonal, a sum of the xi square, okay? And they are non-diagonal element, right? How many of them will be n square minus n? The reason is all of them are n square, the n of them, so the remaining is n square minus n, okay? So there will be, how many of them will be n times n minus 1, okay? And the multiple product, okay? You can put the expectation inside, okay? N of them the same, so that's why I can write in this way. And there will be n times n minus 1 of the product, okay? Expected xi xj, okay? When they're independent, will be equal to expected xi times xj, okay? Because the covariance are 0, okay? And they're the same, so that's why we will be expected x squared, right? Because they're expected x squared. Okay, now n cancel out. Okay, so what you left is expected x squared and minus 1 expected x all squared. Okay, now you put this back into the previous statement. Okay, so put it back to here. So this is what we have in the first set of slide. Okay, and this is what we have in the second set of slide, right? This is the first slide. This is second slide. Okay. What we are trying to see here is, okay, and minus 1 cancel out. So that's why you have this guy. Okay, look at this. N minus 1. So this x by x squared. And the front guy, it's green color. The front guy. Okay. 1 minus 1 over n, right? So it's n minus 1 over n. Okay. And this cancel out, right? N and 1, right? So that's give you this guy. And this is exactly what is the sigma square, all right? Because sigma square is expected x squared minus expected x squared, right? This is what we learned. Okay, so we prove this is true. That's why we need n minus 1, okay? In the other word, if you have sigma hat square is 1 over n of this. Okay. This is equal to n over n minus 1 s squared. Sorry. Will be n minus 1 over n s squared. Okay. That will be n minus 1 over n expected s squared, which is, okay. So if you use this to estimate this, that will be a bias estimator. A bias. Right, this is bias. Okay, because it didn't give you the answer. So that's why we always use this S instead of the version we have in this slide. Is that okay? Let me know if you have any question. Is it okay? No? Okay. Is there any question? If okay, then we talk about proportion quickly. So the sample mean, right, will be or the sample proportion, right, sum of all, will be the good estimator for the population pi, right, and the sample variance, right, will be a good approximate, right, you say good approximation of the sample variance. Okay. So if you're okay with that, then we will continue with the interval estimator. Okay, we're done with the point estimator, then we will continue with the interval estimator. Is that okay? Any question? Now, so we learned that from central limit theorem, okay, the sample mean, okay, will follow a normal distribution with mean, mu, variance, sigma square over n. Okay, this is something from last class. Okay, and we discussed X bar is an unbiased estimator. Okay, this is a good point estimator, and also it's efficient among all the weighted average estimator. Okay, so it's pretty good one. And the question now is, okay, instead of estimating one single point, we want to ask, we going to guess more. Okay, then how do you proceed from that? Okay, so what we mean by interval, we want to be symmetric about the mean. Okay, symmetric about this sample mean. Okay, so what we actually means is instead of giving a point, which is x bar, I want to give an interval, okay, which is symmetric about sample mean, say I want x bar plus m and x bar minus m, okay? I want to say, instead of guessing one point, instead I guess this particular thing, I want to symmetric about this, maybe interval about the sample mean, okay? So what exactly we want to say, okay? And how can we make a property statement about that, okay? Is the following, okay? So we know this is true, okay? Consider the following, okay? I want to look at this minus this, okay? And I want to say the difference between the two, okay? Within some interval, some distance, the probability, okay, is very small, okay? In the other word is, if you rewrite this, okay, mu x bar plus d, x bar minus d, the probability of this is very small, okay? So that's mu here. Suppose I have x bar. For this x bar, I can construct x bar minus d, and I construct x bar plus d, right? I want the probability that will include, okay, of course, should be, sorry, I should not be, no, should be very big. I want this probability very big, right? Because I want this x bar to be different from this, right? The distance will be big. Okay, the probability big. So I want this, right? I have x bar plus d minus d. I want to include the mu, right? Because it's what it means, right? This include the mu, the probability is very big. Okay, or I want 1 minus the alpha, which is I want this alpha very small. 1 alpha is small, small alpha, small. I want it to be small. Okay, this is what we want at the end of the day. So I want, instead of giving x, I want x plus d minus d. I want to figure out this, and I want this to include the mu. And I want this probability to be big. And this with interval, I want to estimate. Is that clear what we want to do? Is that okay? Because it's a random sample, right? So that's why mu can be anything at the end of the day. So that's why you want it to be high probability for this to be true. Okay. And by this central limit theorem, okay, you minus the mu over a standard deviation, right? This guy is standard normal, right? Equal to z. Okay. And if you write this, that means you rewrite this right here, and you divide both sides by sigma over root n, right? It's something we want to do. Okay, that thing is the c. Okay, we want to find what are the c. Okay, up to here, is it clear what we are doing? What we want is to have a statement about interval that trying to include the interval have good probability including the mu. Any question? Okay, so, and we know if Z, right, this is 0, right? And we want, what we want is, we want this area is 1 minus alpha. Okay, and we want it to be symmetric, right? So that means that this area is alpha over 2, and this area is alpha over 2. Okay, is that clear? Okay. And what is this number? Okay. This number, we will denote this number as Z alpha over 2. Okay. And this number, of course, by symmetry, this number will be negative Z alpha over 2. Okay. And we know how to calculate this. This from the Excel will be norm as invert alpha over 2. Okay, so we will show you very soon example, but this is what we want to try to, this is, okay, this is, in this case, it is C here. Okay. In our case, I'm trying to solve for that. Okay. Now, what we want, right? We are this set, this is C, is this guy, okay? So we place C with this, okay? And now what you're doing to do is to rewrite this inequality, okay? Look at this side first, okay? You multiply this to the other side, right? That will be giving this. Okay. And then you make mu to the other side, okay? So that gives you this other side inequality, okay? And similarly, if you do this side, it will give you this side inequality, okay? So you can see by this method, okay, by constructing this method, okay, this interval, okay, will include mu with probability 1 minus alpha, okay? Do remember the mu is a population variable. There's no probability can be assigned there, okay? This is something fixed, you don't know, but there's no probability, okay? The probability lies on the fact that X bar is a random variable, okay? This random variable will depend on what sample you draw, okay? And if you have this procedure, okay, you have 1 minus alpha probability that when you have X bar and you plus minus this particular guy, okay, will include the mu with the probability 1 minus alpha. Of course, we want alpha, the smaller the better. Okay. So it seems like there's no problem. Okay, so let's give you a more definition. Okay, so we will call this is confidence interval estimator. Okay, and this guy will be called ME, margin of error. Okay, X bar, right? And this will be ME, right? This is X bar plus ME. Okay, and this X bar plus ME will be the UCL, upper confidence limit, and this is also ME, right? This will be X bar minus ME. This will be lower confidence limit, and ME is Z alpha over 2 sigma times over root N. Okay, so that is the confidence interval. Is that okay? I guess that would be, looks complicated, but it will be easy operationalizable. I mean, but let me explain again once more the meaning of confidence interval, okay? So you can see we say confidence interval, but we don't have probability, right? The reason why is the following, okay? Let's recall what is the meaning of confidence interval, okay? Suppose I have a first sample, okay? And the sample gives sample mean like this. I mean, maybe I use the same color, okay? I say sample, this is my sample mean, okay? This is the interval I draw, okay? And this is the this is to be the population mean, right? And again, I do another thing, right? I other sample, this is sample mean I have, right? After normalization, right? And again, I have this, right? Another X bar, right? And I do the same for the other sample, I have another X bar, okay? And so on and so forth, okay? And you will see if you have, you construct, you have 100 sample, then you have 100 CI, okay? And if we said we construct the 100 of 95%, say 95% CI, okay? What does that mean? It means that out of 100 of this CI, 95% of them, 95 of them include mu, and 5%, 5 of them does not. Okay, the 95 of them does not. Okay, but we don't know where, but we just know 95% are there, 95% are not there. Okay, but we don't know where is exactly are they. But at the end of the day, we only do one. Okay, remember we don't do 100 of them, we don't do one. Okay, and that one might or might not, we don't know, have no idea. But if we think we repeat this 95% of them, 95 of those are having, okay, so that's 95% we get it, okay? But once we join, we don't have probability anymore, okay? But at least we say with 95% confidence that will be included, but it's not probability, okay? So it's somewhat intricated, but I hope you get the meaning. It means that hypothetically, if we repeat this many times, 95% of those would include, but we don't know which one. Okay. But operationalizable, for operation is very simple. Okay, just the formula. Okay. Here we have standard deviation, the population one. Sigma square is 16, so sigma is 4. Okay. And n is 64, and sample mean is 3. So we want to construct a 95% confidence interval for the sample mean. Okay, that means that the point estimator is 3. Okay, we need x plus minus me, right? And the z table, z is 1.96. Okay, we will do this shortly in Excel. Okay, so me is z alpha over 2, which is 1.96. This is sigma, and this is n, will give us 0.98. So it's 3 plus minus 0.98, so give you these two numbers. Okay, as we said, we'll give you how we get this guy. So let's set the Excel. There's my Excel. Okay. So it's can you see my Excel spreadsheet? I hope you can. 1 minus this divided by 2. And this guy. Okay. So why we have these two? Just to recall, we need this is 95%. Okay. So that means that this is 2.5%. And this is also 2.5%. Okay. What we want is to know this, right, will be Z 2.5%. Okay. How do you do that, right? Because then this is 0.975. Okay. Okay. So that's what we are going to do, right? We'll be using norm standard invert this number. Okay. So that's why 1.96. Okay. So if you're at 0.025, okay. So this is get from here. The green one is here. Okay, because norm as invert is from you give me the probability, I give you back what the Z value is. Okay, you give me the left area, I give you what the value in the Z below. Is that okay? If that is okay, then we go back to the slide. Okay. Any question? So we are going to talk about the very last thing, okay, is what we have shown the interval estimator is not very useful. The reason why is how can we know the sigma square? We don't know, right? We have to use S, okay? So we know that from the T distribution, that's fine, not a big deal. If we replace S to replace sigma square, everything become T, right? That we learned from the very beginning of class. So that's everything the same, right? So everything just, you change Z to Tn minus 1, okay? When you have from S square, you change to, change from sigma, okay? Is that okay? So you can follow the same procedure, and our interval estimator, therefore, will be this one, okay? And again, the same notation. This is margin of error. We are not going to repeat what is UCL, what's LCL, what's the width. You can define the same, okay? So to conclude, today, we give you another example of interval estimator when we have population variance. Sorry, this should be unknown, not known, it's unknown. If unknown, okay, with unknown sample variance, okay? So now the question is, we have the sample size of N20, okay? And sample mean is 3, and sample standard deviation S is 12. The question is, construct the 95% confidence interval, okay? And we know it's going to be x bar plus minus Tn minus 1 alpha over 2 s over root n. This is from the previous slide. Okay. And alpha is 5% here, right? 95%. Okay. And there's a typo in the slide uploaded. It should be n is should be 19, is not 15. Okay, 15 is not correct. It should be 19. Okay, and you get this number. Okay, we will show you how to get this number immediately, but you plug this number into here. Okay, this is the margin of error is this guy. Okay, and S is 12, N is 20, so you get this number. Okay, now we're going to show you why this is the number we want. Okay, go back to the Excel. Okay, so we have N equal to 20. Okay, we also constructed the same. Okay, now instead of normal, we use T inward. Okay, the same logic, but we need to put degree of freedom, which is 19 because N is 20. Okay, and same here, we have T dot inward. Okay, and this guy, the probability is the part N is 19. Okay, and you can see this. Okay, and there's a other shortcut I want to mention to you is, I think there's a shortcut. Okay, you can invert directly this one. I think. No, you cannot do so. Okay, forget about that. So this is how you get this 2.93 in the slide I have updated. And you would multiply this by the S, which is 12, and square root of 20. Okay. So this gives you the margin of error, right? Because S is 12. Okay. And then you can do the same for this one, right? And the mean x bar is 3. Okay. So that's why this plus 3 and this 3 plus. Okay. So that's why the lower limit LCL is negative 0.2 and UCL is 8.6. Okay. And the margin of error is 5.616. Okay. So that is how we have this. Okay. So I guess I should stop here. I stay around to answer any question you might have. So goodbye. I see you on Thursday. And do remember the homework is with you by the end of this month. So bye-bye. Homework is not put upload. Let me check. Is it? Let me check. Yeah, T19 is right. T15 is typo. Yes. Okay. I make it uploadable. Yeah, you can work on the paper and scan. Yes. Yes. Someone asked me whether you can. Okay. Yes. This is you can do that. You don't have to type it. Peter, I think you can upload it now. I guess that's no problem. I work on that. Bye. Thank you.
Hello, Professor。
請講。
係，我想問咧，你嗰個 T19咧，T 個 table 係咪要減咗1啊？因為佢個 sample size
係因為個 interval 係 T_n-1。
哦，T_n-1，哦，OK。
即係睇翻個 slide 嗰度就即係前面嗰 slide 就 T 嘅話就 n-1。
哦，即係 T 就 n-1，但係如果 table 嘅話就唔需要加個。
因為呢個喺上一課講咗個 sample mean 係n-1嘅 degree of freedom， 即係你睇翻 sampling。
好，唔該晒，Professor。
唔使。
拜拜。
拜拜。